In the last video, we were interconverting between wavelength and frequency after introducing the equation C equals lambda nu. What we're going to do now is add in an equation talking about the energy of a wave. And so then we should be able to interconvert between all three: wavelength, frequency, and energy. So the behavior of light kind of took a little while to figure out, and the picture of light essentially was as a continuous energy source, basically to say that it could deliver any amount of energy. And the place where this starts to change is with the study of what's called black body radiation. So in a class like Physics 2, you would probably spend a lecture or more just talking about black body radiation. Here we're just going to talk about it for a few minutes to kind of get us where we want to get in our chemistry discussion. So when we talk about what a black body is with regard to this concept, a black body is an idealized object that absorbs all the radiation that hits it and then emits all of that radiation back out. So it's something we would call a perfect emitter. Part of what gets brought into the discussion about black body radiation are objects that glow as they get warmer. So, for example, right, if you have a electric stove and you heat it up on high, eventually you're going to see that orange-red glow of the coils on the stove. Or if you have an incandescent light bulb, the filament is made of tungsten, and once it's on, you're going to start to see this white glow. So what we begin to understand is that the wavelength of the emitted radiation is a reflection of the temperature. So we can understand the temperature of the object based on its color, essentially. And so that's something that you can think about when you're looking at different stars as well. So something certainly important to astronomy as well. Well, what's going on just conceptually? Why do we see this glowing taking place? The cause of this color leads us to thinking about electronic structure. It's electrons in the matter gaining energy as the object gets warmed up, and then emitting energy as radiation. And it's the emitting part that's important. What we'll find out, and we'll get into this in more detail, is essentially the hot object is emitting energy as photons of light. Photons are massless particles of light, and depending on the temperature, that's going to decide the energy of the photons being released, which will decide what color we end up seeing as these photons are released. So like I was saying, the picture of light at this time is to consider it to act as a continuous energy source, and that would be consistent with a wave. So the traditional approach, treating light as a wave, doesn't really explain why an object is glowing when its temperature increases. And I'm simplifying this a little bit. There's kind of more detail to it than that, but that's the most important point to start out with, that the initial approach of thinking about light as a continuous energy source, just as a wave, didn't make enough sense out of what's going on. So then the guy who's critical in this is Max Planck, and he comes up with a pretty non-traditional explanation where he says that the energy being delivered from a light source is not continuous, but it comes in packets called quanta. So when this object is emitting energy as light, it can't just emit any value of energy. The energy is being released in these packets. And the packet energy is proportional to the frequency of the radiation. So at the time, the view of what Planck said was effectively to say, well, he came up with math that fits the answer to our problem, but we don't really have any evidence that this is obviously the case. So his picture of light is that it's particles traveling in a wave-like trajectory, but each particle is carrying a discrete amount of energy, a discrete packet of energy. And that's really the correct way to think about light. It's a stream of these massless particles called photons, and each photon is delivering a particular amount of energy. So Planck basically runs with this equation where he says energy is proportional to frequency, and the proportionality constant is 6.63 times 10 to the negative 34. I think that's a font problem. It should just be a dot there, not that weird box. Joules times seconds, or joule per hertz. So basically what this equation is telling us is for a given frequency of light, what is the smallest deliverable packet of energy that radiation is going to be able to deliver. And as you look at this, right, this is a y equals mx equation, basically to say energy is proportional to frequency. So as frequency increases, the energy is going to increase as well. And more specifically, we want to say as frequency increases, the energy of the smallest deliverable packet of energy is going to increase in magnitude as well. So Planck comes up with this idea, which we find to be accurate after some additional work, particularly the photoelectric effect studied by Einstein. But blackbody radiation, the study of these glowing objects, really creates a major breakthrough in understanding the behavior of light, enough so that we can say light has both particle and wave-like properties. So remember what I was saying earlier, a lot of the things we're going to say about the behavior of light, we're also going to be able to say about the behavior of electrons. So all this that I'm saying now, we're going to kind of revisit it all as we talk about the behavior of electrons as well. But for now, what it means is we have a new equation that we want to get comfortable using, E equals h nu. Basically saying, if I know about the frequency of an electromagnetic radiation source, I can figure out the energy of a photon associated with that electromagnetic radiation. So it says basically if we have electromagnetic radiation with a frequency of 1.14 times 10 to the 15th hertz, what's the energy of a photon of this light, basically? So pretty straightforward here, right? We have our constant, which will round to 3 total significant figures, 6.63 times 10 to the negative 34, and then our given value, 1.14 times 10 to the 15th seconds to the minus 1. Remember I said think about it as a y equals mx equation, right? So when I think about the units for the constant, it's just like the units you would expect for a slope, y over x. So it's joules per second to the minus 1, or joule seconds. That's the units that we end up with. And you can see, of course, this works out. Seconds cancel with seconds to the minus 1, and we're left with joules. So it tells us that if I have electromagnetic radiation with a frequency of 1.14 times 10 to the 15th hertz, the smallest deliverable packet of energy we have, a single photon of light, would have an energy of 7.56 times 10 to the negative 19 joules. So anytime we have a frequency of this magnitude, that's the smallest deliverable packet of energy that we can have. So we can also work backwards with this equation, right? Go from energy to frequency. We can duplicate what we just did, going from frequency to energy. So the usual, right? You can pause it here and work through these on your own, or Or just let me keep going. Okay, first one's a little bit different, right? Same equation, E equals H nu, but now I know the energy and I want the frequency. So now we're going to rearrange the equation to divide both sides by Planck's constant H. So it'll be nu equals E over H. Energy in joules, that's what we should expect. 6.34 times 10 to the negative 18 joules. Planck's constant, 6.63 times 10 to the negative 34 joule seconds. Joules cancel joules, and I have seconds in the denominator, which will be seconds to the minus 1, or hertz. That's good for frequency. 6.34 times 10 to the negative 18 divided by 6.63 times 10 to the negative 34. It gives me 9.56 times 10 to the 15th. And you can call it seconds to the minus 1 or hertz. Those are interchangeable. So pretty straightforward, right? It's just a y equals mx equation, and this time we were solving for x. Okay, the bottom one is pretty much identical to the one we did on the example. So given the frequency, we want to find the energy. Pretty straightforward here. E equals H nu, no real rearranging to do, just plug in Planck's constant, 6.63 times 10 to the negative 34 joule seconds. Frequency, 3.11 times 10 to the 14th hertz. Hertz and seconds can cancel. Let's see what we end up with. 6.63 times 10 to the negative 34 times 3.11 times 10 to the 14th. Three significant figures, we get 2.06 times 10 to the negative 19 joules. Okay, so hopefully pretty straightforward there, right? Just one more equation we're getting comfortable using. What else can we do with this equation? Well, we can combine together the two equations that we have, right? So if E equals H nu and C equals lambda nu, we know energy is proportional to frequency, and we know wavelength is inversely proportional to frequency. So we should be able to create a relationship between the two. And in fact, we can do it with a simple substitution, right? If C equals lambda, divided by C equals lambda nu, I got one step ahead of myself. That means nu equals C over lambda. So I can, in E equals H nu, just replace nu with C over lambda. Then I can just write it normally, right? And we get E equals hc over lambda, which makes sense, right? It's telling us that energy is inversely proportional, to wavelength. Sorry about that. And that should make sense, right? If energy is proportional to frequency, but frequency is inversely proportional to wavelength, then energy and wavelength should be inversely related as well. Okay, so now we can start to kind of put these pieces together. And conceptually, that means longer wavelength, lower energy, shorter wavelength, higher energy. Okay, let's see what the question is asking about here. It's a long story. You can kind of ignore the first sentence here. Calculate the energy in joules associated with the photons if the wavelength of the X-rays is 0.154 nanometers. So it's basically saying, given this wavelength, let's figure out a corresponding energy. So you can go from wavelength to frequency using this equation, then plug in the frequency to E equals h nu. That's totally acceptable. But this combined together equation kind of lets us do it all in one step. So that's what we're going to do here. So Planck's constant, speed of light, then it's 0.154 nanometers. So I need to make that into meters, so it's however you want to do this, 10 to the negative 9 meters per 1 meter, probably the most, 1 nanometer, probably the most convenient way to do it. Then nanometers cancel and we get 0.154 times 10 to the negative 9th meters. Following our units here, per second goes with second, meter goes with meter, and we're left with joules, which makes sense. When we do that calculation, again, be careful with your parentheses, we get our answer. We get an answer of 1.29 times 10 to the negative 15 joules. So it's saying if the wavelength of my radiation is 0.154 nanometers, then the energy of the smallest deliverable packet of energy is going to be 1.29 times 10 to the negative 15 joules. So I think in the previous one we saw an energy of 10 to the negative 19 for something closer to the visible region, and now with X-rays we're seeing 10 to the negative 15. So you can see, what would that be, 10,000 times more energy per packet for X-rays compared to the visible region. That's why we have to kind of protect ourselves as best as possible when we're getting X-rays, right? If they're X-raying your teeth, they kind of give you that vest to protect the rest of you from the X-rays just because it's high energy radiation. Okay, so then what else can we do? We can go from wavelength to energy, that's what we just saw, but we can also go from energy to wavelength, so we want to be able to do that as well. Oh, it looks like 12 and 13 are the same. I just gave myself some extra space for 13, right? Yeah, that's okay. So we'll just solve these two and that'll be it for this video. Okay, so let's see. Wavelength of 385 nanometers. What is the energy? So E equals hc over lambda. Lambda is 385 nanometers, which is 385 times 10 to the negative 9 meters. So we're good to plug everything in, right? E equals Planck's constant, 6.63 times 10 to the negative 34 joule seconds. Speed of light, 3 times 10 to the 8th meters per second. Wavelength, 385 times 10 to the negative 9 meters. Tracking our units, meters go with meters, second goes with per second, joules is what's left. That's good. Let's see what we get here. Uh, 5.17 times 10 to the negative 19 joules. So visible region or adjacent to the visible region at 385, so around there, 10 to the negative 19 is a pretty standard value of energy per photon. You saw with X-rays it was more like 10 to the negative 15. Okay, the next one here, energy 1.85 times 10 to the negative 19, and we want to find out the wavelength in nanometers. So in the equation, we're going to get a value out in meters, and then we'll have to change it to nanometers. Okay, so if E equals hc over lambda, I want to isolate for lambda, so let me move it to the other side. So E lambda equals hc, and then lambda, oops, I don't know what happened there. lambda equals hc over E. So we really just swapped spots. So when we plug in and solve, right, we're going to get a wavelength in meters that will change to nanometers. Okay, Planck's constant, 6.63 times 10 to the negative 34 joule seconds. Speed of light, 3 times 10 to the 8th meters per second. Then energy, 1.85 times 10 to the negative 19 joules. Follow our units. Joules go with joules, seconds with per seconds, left with meters. Lambda equals 6.63 times 10 to the negative 34 times 3 times 10 to the 8th divided by 1.85 times 10 to the negative 19. 1.08, three significant figures, 1.08 times 10 to the negative 6 meters, but we want to report it in nanometers, so it's times 10 to the 9th nanometers per 1 meter. If I just basically move the decimal 9 to the right, I get 1080 nanometers. Here's meter going with meters, so that's how we end up with nanometers. Okay, and like I said, it looks like all I did on slide 13 is pull that one down to give myself more space to work on it, but of course forgot to delete it off this slide. So I think that's okay for now. So yeah, let me go ahead and stop there. So we kind of seen with all of this the energy wavelength frequency conversion. We'll start on slide 14 in the next video. And just like blackbody radiation, we're going to briefly talk about the photoelectric effect, just so we can understand that we actually saw proof that Planck's constant is accurate with another scientific experiment. So we'll pick up there in the next video.